somewhere in the one of the greatest company in the entire world. Okay. So from MIT myself, we are coming for this particular session. We start from 9 to 12 o'clock. Okay. This will be a very good session. So utilize one of the interactive one. ಸುಮ್ಮನೆ ಕೂತ್ಕೋಬೇಡಿ ಒಳ್ಳೆ ರಿಕ್ವೆಸ್ಟ್ ಆ ರಿಕ್ವೆಸ್ಟ್ ಸಾಮಾನ್ಯ ಸ್ಮಾಲ್ ಓಕೆ
basics machine learning for
ಇಲ್ಲ ಇವತ್ತೈದು ಇಲ್ಲಿ ನಿಂತ್ಕೊ ಮಾಡ್ತಿರ್ತೀನಿ ಅದು ವರ್ಕ್ ಆಗ್ತದೆ ಅದು ಪಾಯಿಂಟರ್ ಸಿಗ್ತಾ ಇಲ್ಲ
ಇದು ಈ ಥರ
ಯಾರ್ದೋ ಇದು ಲ್ಯಾಪ್ಟಾಪ್ ಕನೆಕ್ಟ್ ಮಾಡಿದ್ವಿ ಅವ್ರು ಹಂಗೆ ಇಟ್ಕೊಂಡು ಕೊರಿಯರ್ ಮಾಡಿದ್ದು
So hope you are having wonderful sessions for the past 4 days. Right? So definitely I want to see that this session will give you something extra, will add to what you have learned so far, understood so far, understood so far. In today's session, my idea or my mandate is mostly going to be around natural language processing and how today's natural language processing techniques have evolved to an extent which can directly be used as application in any domain, like the one that we're talking about today, in healthcare or medical field. And between these two, the NLP technology and medical domain, we have IoT, which is trying to have a interface between these two areas, right? So one side of this overall ecosystem is you have the end application, which is where I want to see how I can make use of the current technology for the healthcare, right? Via the devices that I am using in my day-to-day life. As an end user, you will think of this. On the other side, the professionals, I mean the medical professionals, healthcare professionals, researchers, right? Doctors, laboratory experts. So they want to see how these trending technologies can be explored to improve their day-to-day activities, maybe in handling patients, serving patients, helping patients, monitoring, diagnosing, right? All the things that they do regularly. So they want to make sure that we have to reduce the effort in our day-to-day activities, not to reduce their work basically, but to improve the quality. Improve the quality in the sense that I want to give the medicine at the right proportion, at the right time to a person depending on his condition. Right? So see that the healthcare is available to everyone every day. Is what is the overall idea. So these IoT devices, because we know that we are connected with each other through the internet, through the devices that we use. So all the devices that the digital devices that we see we are in touch with are connected to the internet, right? Be it our mobile phone, right? Are the gadgets that we are using around, like the smart home devices would be. Right? All these are connected to the internet. That means they can be accessed from any location in the world, right? So when it can be accessed from any location in the world in real time, so this is a wonderful opportunity for people who want to make impact onto people's lives. Like you are getting somebody's data, how can you help him? Especially in the healthcare, a doctor sitting somewhere in US, they can treat a person in India, right? Just by seeing the data that we have gathered through continuous taxation, like streaming from the digital IoT device across the world. So, going a step forward, we also want to see that we should be able to communicate with these devices with maximum easiness. Like, I should be in a position to interact with these devices as if I'm talking to a person, right? Assume that you are talking to a doctor who is explaining your difficulty and he is listening to it, he is making note of it, and he is guiding you back on that. So now the situation is I don't want to physically go to a doctor because of many reasons. Time, right? Or the distance that I need to travel, or his availability, right? All these matter and the real time decision making. Like if I have to meet him, like he's an expert, he is in some different geographical location. I cannot directly go to meet him because of all these constraints. So I will talk to my device, say a phone, and he is able to receive it and he is able to give it back. So one solution, simple solution is through the way of organizing that we might have done. Like it is pretty common nowadays, like video consultations with the doctors, medical experts. It's pretty common nowadays. But for that also you need to book an appointment, be available at the slot, right? Can this be further improved? Can can I assume from virtual uh, professional that means is not a real person respond to me for the problem that I have if I just ask the question first. So that is where the natural language processing technology comes into picture. You interact with your device in your natural language and your device is expected to capture that, right? And the technology sitting behind needs to analyze what you have said, right? And think of what is the potential solution or the kind of the diagnosis that is possible for the symptoms that you have quoted and respond back or probably speak back. So this is where the natural language processing technology is now getting into the healthcare domain under the IoT. Okay. So I'm trying to mostly cover these parts. I'll try to give you the overview of different applications that we are seeing today under this problem, and also take you to the technological concepts. May not be in so finer detail, but with much detail sufficient for you to understand how this exact technology, the state of art, natural language processing technology is working behind the scenes. Okay. Maybe at the end I will try to give a demonstration of this. Okay. So in today's world, when we talk about natural language processing, we mostly will be talking about the large language models these large language models basically are machine learning models implemented with deep learning techniques. When I say deep learning techniques, mostly I assume that from the past 5 days of present, you must have understood what is deep learning and what is machine learning and how the ML models are being developed to solve different problems. So, just to uh, take you back to the interesting definition possible, machine learning is just a set of techniques, algorithms, which are used to automate certain tasks, specific tasks, right? Could be like recognizing a person, when you give the face image, right? Or could be classifying the different objects in your scene. So I want to train my machine to do these different tasks. So we have several techniques based on the problem and based on the problem data, like whether you have annotated data with you or not. We have different techniques. So deep learning is a subset of machine learning, where we train neural network kind of model, and deep learning has its applications in different domains. And NLP is one of the application area of deep learning or general machine. So now, uh, you can just imagine that LLMs are the AI systems trained using deep learning techniques on vast amounts of text data to understand and generate human language. Human language means the way we generate, we talk in the language of RFS, whatever language it could be. But mostly the focus is on English, which, as you all know, that it is like mostly used language today. But then we have several other types of language models being trained where being used for other languages too, like Indic languages. We have today just are saying there's some new LLM that is being trained for Indian languages. Okay. So there are progress happening, but mostly the stable ones that we're seeing they are for English. So uh, these large language models, why we call them as large? Because they are in fact large in their size. So they typically have parameters ranging from 1 million to 200, even 300 million of parameters. Okay. So if you just imagine a simplest ML algorithm, which is a linear classifier, right? A simple regression algorithm will have parameters equal to n and the number of dimensions in your input data. So the number of dimensions is basically the number of attributes with which you have represented your data. Like I am going to represent chair. So what are the features I give the chair? Height and width and maybe the length of the so you can just count the number of features that is the number of dimensions. Okay. So how many features you have given to describe your input, to describe your data? That is the number of dimensions, and that is the number of parameters. Mostly directly proportional to that in a simplest algorithm. Whereas here it is billions, in that of billions, irrespective of what is the dimension of your data or original resource. Why? Because one common observation with ML models so far is as you increase the number of parameters, you can see the data from many different spaces. With many different transformations. Okay, some objects you won't be able to recognize if you see it in this particular. If you change your position and see that, you may recognize that. That's a simple transformation. So I'm standing here I want to be able to see a face here you are typing. I will just reposition my foot with a simple translation, right? One translation. Maybe such many different transformations, right, which are defined, but here we are talking about those transformations which are not exactly defined under mathematics, but to be like once you see those transformations, you can define them, but they do not work on the defined transformation. They define their own transformation to make sure that they see the data clearly to achieve the desired task. Right? My job is I want to call this as chair. Okay? And I will give this chair image as input. That is just the pixels, right? Arranged in matrix form. Pixels is basically the intensity values considered transforming different channels, like RGB or whatever color state that you show. But now I am asking my model to learn whatever possible transformations on the image of the chair to finally be, you know, be able to detect chair under an environment with multiple other objects. So in this environment, I have tables, chairs, people, plants, many such objects, but I want the model to explicitly identify where the chairs are. This is it. So to cause a chair or to recognize a chair, what all transformations you want to apply on this data, in this data you want to. So when I say what all transformations you can apply, it says I want to apply 1,000 transformations to completely justify my decision. So 1,000 transformations comes with 1,000 different transformation matrices, right? And each transformation matrix would be on size, like as simple as 110. And then there are some numbers, let's say 1,000. So 1,000 by 1,000 matrix would be one transformation matrix for you, plus 1,000 transformation matrix, just multiply how many times that's billions of parameters are involved in these large language. Okay. And that is the reason why they are so capable in achieving general intelligence. When I say general intelligence is something which the living things uh, have with them. Like I have math questions and few things I have not explicitly learned, but I can do them. Right? That is because I synthesize the learning and apply it on a new task that is given to me. So if at all that I am given a new task, it's not 100% perfect in achieving that task. I'll be better than a person with no knowledge. I'll be at least like 60-70% good in doing that job, even without having any explicit training on that particular. That is the revelation. So, till today, whatever ML models that we have been building, they were built for specific tasks. Okay, detecting change, a model to detect a change. Okay, recognizing a face, a model to recognize a face. A model that is built for recognizing face cannot be used to recognize change. They are so problem specific, right? They do not process general information because they were quite small in terms of number of parameters and the kind of transformation that were being used in those models was so limited and mostly defined. Okay. Suppose if I go to conventional learning techniques like support vector machine, even support vector machine we use for non-linearity, we use certain non-linear terms which are defined terms. Right? That means they do a specific transformation onto your data. There could be certain parameters to just align those together, but still the transformation is uh, overall that is going to be one specific transformation. But here they are not defining any transformation. They just give the data. They are saying that I want to do this. Okay. I am giving a image, I'm calling that space. I'm giving a chain image, I'm calling that shape. Okay. In between, whatever you want to learn on this data to identify finally that this is space, this is here, this is up to you. That is how the model is created. But so to do that, you need to have very big models. So basically, these are neural network models. Neural network models, maybe you might have uh, understood by now. They are the machine learning models which imitate human brain. Human brain is made up of several of billions of neurons which are connected and which do the task, and some neurons get activated based on the thing that you are doing, and finally the decision will be taken based on those activated neurons. Right? So there is a similar energy was taken onto the neural network. Okay. So this was built on that idea of human brain. Uh, so human brain has billions of neurons, and so it is so complex. And it is able to achieve complex tasks, and we are doing the same in the deep learning. So with this background, if I come back to the initial thing that we were talking about natural language processing models, which are large language models, are in short LLMs that we are talking about, which are deep learning models, basically with billions of parameters, right? Ranging from 1 billion to 200 billion. So as the number of parameters is increasing, we are saying that the capability of the model is also increasing. So specific to NLP, the models that we train, the LLMs that we train, they consume text. Right? When we talk about natural language, mostly the format that we define is the text format. So when I say these large language models are so capable in doing NLP activities, so the capability has come to them because of the training that has been carried out with huge amount of data available on the internet, particularly the text data. So they've been trained on, they've been trained on, you know, petabytes of data, text data that is available, like entire Wikipedia, right? Entire social network conversations. Definitely, after removing the sensitive information. Okay. So all such text data, whatever post, right? Movie analysis, reviews, whatsoever text data that is available on the internet today is used for training these models. Basically to understand how the text is, like basically to understand the language, understand the text. Not to do any specific task. It is a general training that happens on the evidence. Just to understand how the words come in text. Basically, to understand the language. For you to communicate in any language, you must know the language first. You must know the words, you must know their tokens, you must know their linguistic rules, the grammars, right? All these things will be learned by your large language models that will make meaningful. You don't teach grammar to it, but economic grammar itself will be better. But for it to learn this language, it has to be
Hello.
billions of
Everyone.
text phrases. Okay. So that is done in the training of these models to pursue these capabilities of learning from text. So when you get new text to it, it learns on top of it. It tries to understand what the text is. Next, as you do, when I give you some research paper to read, it's not 100% because you are not from that domain. At least you will understand what the overall area is. Even though you do not talk about that and knowledge, you are capable of understanding from that. So that capability is not present. And understanding language, which is basically what it means for. And generating text, this is very important. Like in great, if you ask him to describe something, just go on describing. if you ask it to write a story, it writes a story. Could be hypothetical, but it writes it. Could be a very simple living in a, we call it a hallucination in real terms because that is not real, but it just writes it as if it is real. So that is the capability that it gets through training. Various uses apart from this, ranging from translation. I am good at Tamil language, I want to understand Tamil language. Even if you want to translate something into Tamil language, translation capability, because it has not been trained only on a specific language. It has not taken only English as before, but nature content is English. Apart from that, also that we trained with other language text. Okay. So you can translate, you can summarize. You give it a book, you give it back. Depending on which you can process so many information and then the computational capability. Okay, that's the constraint that for it to work, you should have a strong computer, basically the GPU. Q&A. You can ask it some question, it will respond back, basically it will that, yes, assistant to chat. Okay. So you can definitely now think of these elements as super smart language experts that have read almost everything on the internet. So, and are ready to help you understand, write, create new text. They may not be perfect, but over time they are getting improved. And then you also use them um, into the fields which are very demanding with respect to the accuracy of the information, right? The correctness of the information, the legitimacy of the information, then you must adopt them to your domain for them to work. You know, otherwise they work, but they sometimes, they sometimes just generate, unrealistic things. So that it's very dangerous in some cases, like especially in the real. So they are capable, they know the things, but they may not be accurate with respect to everything that you are expected to work on. So that they want that some kind of further adaptation of these to your domain. You can talk me in between that if you think it's something that you don't understand, or if you may not understand a particular thing, so it's better to get it clarified when they refer to the next subsequent content you will be able to right? So now I'll straight away show you the advances in this with respect to IoT, conversational interface. This is where we are seeing like there are lots of conversational agents, something like virtual assistant being used in medical domain. You might have seen like through the other applications where you just need to ask your particular question and then respond back. Like you may describe yourself and you will say, okay, this is something with a particular address that our problem is, and these are the kind of readily the things to be followed to get it done. So it's conversation is or if not that expert level conversation, at least to level where you can at least ask it, here is the doctor, it's just the available for time. Applications. So that's the best. It is not very effective medical domain, but then they are not medical domain. This is what. You can just give it a summary give your details of your symptoms and what you have been observing with your body for past 5 days, and will come to the conclusion and give you the response back. So that's the conversational ability. Contextual understanding. So contextual understanding is where like it builds because I mean, you have interacted with it for some time and it has seen and observed your behavior, the context with which you are talking, and your past negative data. With that information in hand, it should respond back to your present situation. It is not that just that, it is responding only looking at your question, it is responding along with the additional information that is captured over the period of your conversation. Right? So your behavior and the knowledge information you are asking everything. You might have uh, seen the smartphone devices right? So we it like if you have used it, you must have learned initially only that related conversation with you. But with time, it gradually adjusts to your kind of behavior and it will come to know if you are asking something what exactly are you asking because of the past conversation, right? Uh, so it will resolve several conflicts in its responses based on your past conversation. So if you are asking about, okay, this turn on sunlight, it will come to know which side are you talking about based on your past. Uh, Something like that in medical field as well. So we have contextual aware conversation based on the past conversation. So multimodal NLP. Multimodal NLP is where the NLP model of not just taking text as input but also like each content as well as input. Providing that. This is in it's good shape today already. So definitely when you come to see this and this way we can just post it in any like you are talking about some thing related problems, right? You may not be able to describe 100% in your text. So it would be better for you to just capture an image of the place or something like in part and post it with your conversation for a better clarity. So the LLMs that we are writing model LLMs, model some different modalities, the different modalities of text, images, voice, right? Images is design, sensor. So all these are different modalities. So X-ray could be one image. It is not a normal image, but it is modality. So the elements that are being now considered, at least the domain-specific elements, they are now given capability of understanding data from multiple modalities. So airspace NLP is a very important problem in medical domain, at least for the real-time information. Because whatever the large language model that we have today are very big. As I said already, because they are big, for them to process your input or your request, it requires huge computation, right? And just for them to be up and available, it needs computation. But that is possible only if you are capable, right? Of having that. But as an end user, you do not want to ask, you cannot just afford. So the healthcare provider, they are coming up with these applications which are just installed on your device, something like that you are operating on. You have a single app which runs on your device and which makes the decisions on your device itself. Or is limited memory. These are called as edge devices. Okay. Maybe another if we camera, I just want to have a face recognition model on it. So these edge devices will have limited memory, limited computation, but for your language models, which are large over, they are not so big now. So today we are seeing shift also for them to be using these edge devices by doing a lot of size shrinking because the levels are trying very big sessions and I think huge model is not required for very very fine problems in the overseas this already possible. So we can shrink the size, right? And we can do the inferencing on say like for example if you are doing the computation in real numbers, I can convert it to integers and do the computation. This is a lot of fractional accuracy. I will be having the same model after working in lesser memory. So such types of uh, optimizations are happening to take these huge models onto the devices which are having less computing. So that yes, saves energy. So privacy preserving energy, like you may not be so happy to share your data on the net, which is your personal data, like whatever your symptoms are, so like medical conditions are. You don't want to just share it because you think that it's confidential or something you don't want to share across the internet because you don't know who all can access it. So basically, today we are also seeing the techniques which are kind of developed and they work only on the body devices. They take data and process them only on the body devices. And only the encrypted values will go on to the actual differences or the computer machines will get the processed data or further processing and information. So from the process data what I mean, so you won't be able to get back to the original data. That is operated with encryption and all. So, transfer learning training model. Training model is basically the LLM that trains officers without any specific domain in mind. It's called pre-trained. Whereas transfer learning is a technique where you take a model developed for one domain and you reuse it for another. Okay. A model which is developed for recognizing say the vehicles could be used to uh, use for an application like recognizing other like animals, because basically the knowledge of recognition requires capturing certain features of the object. Okay. But when you change the domain, there will be like several features which change from domain to domain. So you need to adapt to that. So, but mostly when you keep on the neural network perspective, neural network is kind of like stacked layers of uh, neurons. The initial layers of the neural network will basically cover the foundation about the data. The numerical layer at the end will have the information specific to domain, the specific problem, and at a very high level. So, in the transfer learning, what we do is instead of training the model again from scratch, we take the already trained model. Okay. Coming to the new problem, we do not alter the initial parameters. You only try to see that the last few layers are updated. Basically, the training of neural network is to decide what are the values for the different parameters that you have in the network. When I say 1 billion parameters, at the initial point, those 1 billion parameters are completely random. They are randomly initialized from some distribution that time. But through the iterative training that we do with the data, those parameters get updated iteration by iteration, finally to a level that those all the parameters together are achieving your desired. So if you can avoid training or fixing the value of those initial data. Then your training time is mostly half or even less than that. Because the unit for training itself will take data time depending on the model size. If, for example, if it is a 70 billion model, the 70 billion model with typical good infrastructure will also take even 12 months process to be trained. So you can avoid that by creating the initial data. So that is the transfer learning thing. Even the transfer learning is used to adopt the existing model onto the healthcare domain. Is what I need to take care. So emotional sentiment analysis. So basically through your interactions, it is the models are also coming to identifying those emotions through the text, right? And the sentiment that happen you are like related about this response. What exactly are you thinking with respect to your privacy? So the models are now able to recognize these things. Content language translation. This is specifically helpful for interacting with different experts who doesn't know your language or where are you do not know the language at the end. So these barriers have been removed with the help of these translations into the real time translation of the text that you input to the text that the other side translates. So So without all applications that you can that use with respect to the medical design from the large language models that are available today, uh, it obviously makes sense for you to first understand how these large language models are built, what are the basic units of your large language model. So today, LLMs are trained on uh, various foundational block, and which is the most important block for us, the transformer architecture. So transformers was introduced like in 2017 as a level architecture, which is used to train very short deep learning models. Okay. This is being used in both image domain and in the text domain, in the so, whenever will be, um, so in the transformer architecture, basically you might be wondering how these machines are using the text data as input and how are they processing, how are they learning the context inside the text, how are they trying to understand the language correctly. Basically, these are the units that are responsible for that. So as you can see in the left side, we are passing the input with a particular text. Okay. Let's say one sentence, right? So this input sentence model input to this architecture. Okay. Because our computer cannot read the text, maybe a video something other than number. So we need to convert it to number, some meaningful numbers, which is called as embedding. So embedding is basically like there are pretty uh, very much able embedding that we are using today, uh, like word model or more. So they give vector representation to words, and those vector representations is given to the model based on the context in which these words are. So basically, the embedding process is to convert the text into a vector, a real vector. So if you have, say, for example, 5 words, for each word you will have a vector, and those 5 words will have 5 vectors corresponding to that. This will go our attention block. So as you can see here, to the left side, so whatever the block, the block that you see on the left side is called as the encoder of your transformer picture. So the encoder basically tries to encode the information present in the text into vector. So that later these encoded values can be taken to do the corresponding decoding. The decoding may be done for various reasons. It could be translation, then the decoding into translate the new input into other language. It could be summarization to share the content, or it could be to classify the given text into say it is a review. I want to classify the review to ask you on the review so that it may be decoding. But basically here in the encoding, we just take the information and we are trying to learn and get the context of it and try to represent it in a context aware way. So, so this encoder architecture involves a very important component called as attention. Attention is basically, if you go to the next slide, attention is basically to see how the words within the given sentence are related to each other. So, if you want to understand this sentence, for example, the animal is not wrong, will become to right. Now, in this sentence, the word equal, right? What is it representing? Is it the animal or the spirit? Animal, right? So, attention, self-attention is basically to look at the other words in the sentence to understand or to represent this kind of word. Efficient, right? So, I mean, the language model has to understand what the word meaning or which exactly the other word is, which is more relating or more close or more important for this word. If you say the same sentence, the animal did not cross the street because it was too wide. Not tired, this case it was too wide. Now the same sentence, just the word, the last word is replaced with wide instead of tired. Will change the it to representing from animal to the road. The animal could not cross the road because it was too wide. So it is now representing to the road. So the context in which this word has been used, the word fit has been used, is defining what the word is. Okay. So to learn the context, the model, I mean basically to learn or understand each and every word within the sentence, or represent each and every word within the sentence, it has to look at that word with respect to all the other words around it and see in that context what this word is meaning. So that is called as attention, and it is self-attention because this you are not looking at any other thing other than your text to decide the representation for your words. So that is the self-attention. So this attention mechanism was introduced which after having in initial before this transformer architecture, what we had in NLP was to handle this sequential information. Text is basically the sequential information, right? Word after word. So to understand the sequential information, the models that we had were like sequential models are basically your LSTMs, LSTM architecture was there, and we have RNN models. Uh, those models, when compared to these attention-based models, the working of those models is they used to see word by word. They do not get to see the entire sentence in one go. Instead, they think that they is coming with respect to time. The data is coming with respect to time. And now, in the time step, for example, you are in the time step T, you have observed the data of 2 times 50 minus 1. You have learned something out of it. and you are deciding what this present word is. You are representing this word based on the information that you see so far. That means at every time step you are aggregating the information, you are trying to represent whatever you have seen so far. Right? But the problem is when the sequence is very big. I want to understand a word which is in the last line of the page by reading through the complete page. So your model has seen all the words of the page from top to bottom, and it has reached to the bottommost word, and it has represented every learned so far. The representation is basically in some vector. It is represented in some vector, so which we call as in the hidden context vector in ML terminology. Right? So the problem with those models was we had the problem of forgetting. Whenever I see something new, the old information was erased to some extent because of the new information. When the sequence is very big, the chances that the model forgets the content that it has seen initially will be very high. Okay. So for because of this problem, we were not able to handle the use of large length, and there was another problem of vanishing gradient problem, which is basically one big problem with networks, which is where vanishing gradient is basically in the neural network to update your parameters every year, and the parameter updation happens in a with an algorithm called as back propagation algorithm. Back propagation is basically you take the loss of the model at the last layer and you try to adjust the parameters from last layer back to the initial layers, right? With the help of gradient descent optimization. So when you do with gradient, basically you try to differentiate your loss with respect to those parameters. So when you have deeper networks, when you start from the last layer and try to differentiate those loss values, right, it will become a chain of differentiations, right? And the value that you get out of differentiation is the gradient value. And when the values become smaller and smaller, because of the huge chain of multiplication of the smaller values, the values in the initial layers, the gradient values in the initial layers will become almost zero. And because of that, the parameters of the initial layers will not get updated. So with that problem, the gradient becoming zero, that's the initial gradient problem. That was another challenge that we were seeing in the sequence processing. This self-attention mechanism was a solution for both of these problems. And this self-attention mechanism was strongly used in the transformers architecture, which is basically that it is not seeing the information sequentially, but it is seeing it as a whole and trying to learn each and everything by looking at each and everything. Okay, so this is how it works, and that's the reason why it also requires huge memory as well and computation. If you come back to the previous slide. So attention is that for every word I need to come up with the representation, and that representation will be decided based on the other words in the context, and which word should be given how much importance for this current word in hand is decided by the attention mechanism. Okay. So now, once you have that attention vector computed for each and every word, so we are going to normalize that and forward that information subsequently, and that is the encoded representation of your data. But basically, transformers use an additional capability to attention, which is called as multi-threaded attention. That is where in we try to adjust the parameters in different ways to get attention vectors of different type. Basically, it's kind of you apply multiple transformations onto the data to see the data in a careful way. So multi-threading basically you do the attention mechanism with different weight matrices. Okay. So if you go to the next slide again, um, what you can see here is how the attention works is basically for every word we will have a q is a query vector, k is a key vector, and v is a value vector. So these three vectors will be initially randomly chosen, and you will have the weight matrix that is computed with your mining, and the query and key will be multiplied and scaled up for normalization. Okay. And masking is done in the decoder stage only. So softmax is used to take the activation between 0 and 1. Basically, the important values for the word should be in the range of 0 1 so that we can have better limits. So finally, this same process is applied with different weight matrices. When you say different weight matrices, you have different parameters. So with the same query and key value vectors are multiplied with different weight matrices, you get different representations, and all of them together will give the overall information related to text data. So that's the important architecture that is developed from that. And the next is feed forward is a single linear layer, maybe stack of linear layers that you organize, and followed by the normalizations. So this entire block is called as one encoder generator. Okay. Your attention, multi-thread attention, and scaling and normalization followed by the feed forward layers followed by the normalization. So this together is one encoder unit. These will be repeated. So you will have the data encoded in first encoder unit, then the output of that encoder unit will be given to the next encoder unit, and you will have different weight matrices over there. And the overall training is to identify best values for this weight matrix. Okay. So, in the transformer architecture, there were 6 encoders units, followed by 6 decoder units. So, we understood what the encoder does. And coming to the decoder part, in the language, in the LLM language training, is basically there is no expectation kept at the end. You do not have something like okay, this sentence is positive, this is negative. No, you do not do that. It is a simple casual language training, which is basically to predict the next word in a sentence. Okay, I give this word, predict the next word. So, what is kept in the output is one word shifted right. Means the next word is kept as the output. So the vectors that you have computed out of the encoder will go to the decoder block, and in the decoder, just the thing is that you do not want the model to see the next word also in doing the attention area. Because in the attention, I told you that the current word, if you compute the vector for the current word, you will see all the other words. Because in the output, I have the next word to be predicted. You will just mask the words. Okay. Mask is you just declare the word by random from specific token. Like you call it mask here, and you try the same attention mechanism. So one extra thing that you see is like you will have one masked multi-rate attention followed by one normal multi-rate attention, then followed by the same feed forward that means basically a sequence of linear layers. Okay. And at the end you keep the softmax and the class probabilities. Basically, at the end the probabilities are computed for each and every word in your vocabulary. Yes. So these large language models, they will maintain a vocabulary of all possible words that they have seen so far, and they try to assign probability to each and every word in that vocabulary. Okay, and the word with highest probability will be chosen as the predicted word, the next predicted word. So our expectation is whatever word is there in the next position of the correct word should be predicted with highest probability. So you train the model and until unless you see that next word getting predicted for all the sentences. Yes, so your well text predictions and word predictions, they are just basically word completion models that you see here. I mean, what you start with some characters, like 3 4 characters, it tries to complete the word. So that is one. And second is just the cache-based text word prediction that is being over here. Basically, it will have in the cache some text phrases that you have used and based on that it tries to predict. But here is actually for the whole bunch of text, it will really give petabytes of text data to the model and it is able to detect the next word for the entire text data that has been given. So until it achieves that, it will be trying, iteratively. I mean, what the meaning of trying iteratively is, you see what is the loss. Loss is basically like, okay, is it predicting this word or not? So if it is predicting 1, otherwise 0, that's a plus tag. Okay. So all in all, you will compute for how many predictions, how many were correct and how many were false. So that is your loss, and you try to put it in simplest way possible. You will backpropagate that loss to adjust your weight values so that the predictions can be better. Okay. So if some importance is given, I mean some word is given more importance in the prediction, but it is wrong, you try to reduce the importance by reducing its weight. So when the weight is reduced, automatically that word will not get populated and that will get suppressed. On the other hand, some other word will get populated. So by doing this iteratively, like thousands of times, ultimately the model tries to come out with the weight matrices, the weight values, basically the parameters values for all the layers. And when I say weight matrices, this is what the parameters in the model. And if it is a 70 billion parameter model, you can say that. That means you will have total weight values equal to 70 billion from all the matrices that we see in the deep architecture. So until those 70 billion values in your entire architecture are finalized, the model is just iteratively trying and the weights are continuously adjusted. It is not a random adjustment of the weight, it is a selectively adjustment based on which gradient is going how, right? The gradient values are very high, then the corresponding weight vectors are they penalize the values will be reduced. Gradient is high, you have a very big difference from what is expected, and that is going to penalize your strength more. So just take this as a simple way of understanding it, but it is more than this in the actual implementation. Okay. So now this decoder will also be like in the multiple edges. So you have stack in decoders, in this case like 6 was used in the initial transformer architecture. So you can play with it. So you have encoder, you have decoder now. You can just go on placing them in sequence depending on your compute capability because each encoder decoder unit will have, let's say, depending on your input dimension. If one encoder decoder requires say 50K parameters, then it can require 500K. So if you can process such a big model, then you can think of having 10 seconds. So I just gave you some simple numbers. So you can compute that. Will depend on your input dimension and what the number of the heaven index that you have in your architecture. So all that will matter to compute the overall number of parameters. But as the number of parameters increase, the computation power will also be expected more. Softmax is this simple operation. So softmax basically the query vector and the key vector. Query is the word that you are attending currently. So in our case, like, to decide which is more important for the word it in a column 2. So that is my query. I want to decide which word is more important, I mean, which should be given more weightage. So as you can see, the dark colors are corresponding to more weightage, light colors are less weightage. So query Q is your vector corresponding to the word IT, and K is the key, I mean each word one at a time, and the denominator is just to scale down the value because the dot product Q K transpose is basically the dot product of two vectors, which will be which might be of any fixed scale. To reduce that scale, we do the denominator multiplied by V is the value vector that is the importance that will be given back. So softness of it will bring the value back to 0 voltage. Okay. Next. So this is what the multi-head attention I was talking about. As you can see here, so all the computations are done using matrix multiplication basically. Like you have two words, thinking machines. Thinking is one word which is represented in one vector using any embedding technique, and machines got another embedding. Okay, and the expectation is the dimension of the embedding vector should be of same size, just for the ease of computation, so that we can do matrix multiplication. Okay. Here, this is what is the like as you can see here. So we have 8 heads. So each head will have one set of matrices. So one set of matrices means one set of transformations with another set of transformations. This multiplied by this will give you one transformed vector, again another transformed vector, so that I can see the data in all possible ways and try to represent or learn the content within it. Okay. So here you see W naught Q. I mean this weight matrix is fixed, whereas QKB. Q is the query word, in the word that is in the current position that you are trying to represent. K is the words in the sentence. So you will have K ranging from first word to the last word of the sentence. V is the final value vector that we are trying to compute. So these three will be initially randomly initialized and they also get computed over time. Okay. So again, similarly, another weight matrix, one more weight matrix. So totally, you can think of 8 weight matrices. Any number of weight matrices basically. Multi-head means multiple such weight matrices. Okay. And each will give you one vector corresponding to each word and a matrix. So because of 8 matrices, you have the word thinking represented in 8 different vectors. And similarly, machines are represented in 8 different vectors. And I do not want to carry multiple representatives of each word. So the simplest way is we just do the concatenation. Okay. And this concatenate the Z here, we are just trying to put them one after the other to have a single vector. Okay. So now this vector that is computed will go to the linear layers, the feed forward. Okay. So this process will be repeated at each encoder layer to finally come out with a better representation. So the difference between the conventional sequence model like STM, GRU or RNA when compared to the transformer based on multi-head attention is in the decoder, the decoder, every decoder unit will see output from all the encoders, okay, for all numbers, so that it can decide which word to be populated easily. If you take a translation problem, for example, you cannot translate word to word. I give you a sentence in English. If I ask you to write a sentence, same sentence, for example, in Kannada, okay, you will not expect the first word of English sentence will be just replaced by its corresponding Kannada translated word in the Kannada sentence as a first word. No, it will not happen. So because the language rules of Kannada are different compared to English. So it's true for other languages also. So you cannot expect the decoder for the first word to just take the encoded value of the first word and predict it. Instead, it requires all the decoded and encoded vectors of all the words in one go. So whereas in the conventional approaches, models like RNN models, we just aggregate the information at every word into a single vector. So what the encoder is to give in RNN is only one vector for the entire sentence, and the encoder has to predict the entire sentence by just having this one vector. Okay, which is having the aggregated information. So that was one challenge because it doesn't have the fine-grained details of each word, and so here we are capturing them separately. It is accumulated as separate vectors and they are fed into the decoder and it will play it. So this is solving the problem of this translation problem very effectively, and also the long sequence handling problem. So in the case of panel, as I said, if the sequence is very long, the final computed vector will have the information of the most recently seen words. Okay, the information mostly will be the most recently seen about the most recently seen words. The initial words of your sequence might have been errors because you just go on one and it is so true with all models, right? Whatever we have seen very recently, when you will remember compared to what we have seen like yesterday or day before our meeting over here and all that. Unless otherwise it is a very important situation which is just being flagged in our mind. Okay. So this is true with those RNA models, and this was a problem in these kind of large sequence handling use cases. So this has been solved here because irrespective of the length of the sequence, you will have all the values. It is nothing like you have that the information has been vanished. No. Only thing is the computation will be huge. This is made possible because of the dimension of bigger and bigger GPUs, TPUs, and huge computing devices today, when compared to the devices that we had those days today. So higher and data architectures were introduced. Those were the state of the art at that time, but as time passed, we have better computing devices, and so the architecture has improved. Okay. Go to next. So this transformers is the foundational work. Again, the attention mechanism, especially inside transformers, was the foundational work of all the large language models, or I can say all the foundational models that we are seeing in all the fields. Like in computer vision field, we call it as computer vision based foundation models. In language processing, we say large language models like that. But these attention mechanism and transformers, these were the initial works that have led to these inventions of present days large language models. Okay? Why? Because whatever large language model that we are seeing today are either using the encoder representation of this transformer or the decoder representation of this transformer. So one such category of large language models where the encoder units alone are used in the entire architecture is the bird-like models. Bird was introduced in 2018, which is basically on top of transformers architecture because but it has just used the encoder units. It has not used the encoder units of the transformer. It has just stacked up these encoder units and the training was done. Okay. So as you can see there, the word play models were trained for two tasks. One is the next word prediction, and second is next word prediction is called as casual language modeling (CLM). Second task is next sentence prediction. Okay. So mostly here, the text, whatever text that entire Wikipedia, the entire internet text was captured, and they were split into sentences, paragraphs, and sentences. So you know that if a Wikipedia article has a paragraph, that means you will have sequence of sentences, not just sequence of words. The next sentence mostly depends on the content about the previous sentence. So next sentence prediction is another task that was included here in the study of uh, the bird-based large language models. So it basically, you can think of that, we have seen the encoder units of your transformer. You just stack up those encoder units. Okay. At each encoder unit, you will have one output. So you can use that output. So it's a translation problem, right? If it's a translation problem, so all the encoder units will populate some values, and the final encoder units will populate the final translated values for the given sentence. If it is a classification problem, something like sentiment analysis, I have a product review which is one sentence, I give you an input and you have to decide whether it is positive or negative or neutral, for example. So you just pass the sentence, and every sentence here while training was appended with one specific function called CLS token, which gets all accumulated information from all the encoded values of all the words. So while taking the decision, you take the information from that token or CLS token, and that is used for the classification problem. Right? So it is time basically but the basic trend, so every large language models will initially be trained for only one or two tasks. Once the very one task which is used is the casual language model, which is next word prediction. Without any explicit problem, you have the text with you, any book, any paragraph, any HTML document, or any read, any chat, you have the text with you. So given this sentence, within the sentence, given this word, predict the next one. Only that. Based on that only, all the elements are trained. Okay. Next one is these word architectures are trained for next sentence prediction. Okay. So these are the initial training. Once this training is done completely, then the subsequent task dependent training will be done. Okay. So the well-known tasks, at least to measure the performance of these elements that are being produced, are like the summarization capability of them, okay, classification capability of them, question answering capability of them. There are a lot of benchmark data sets available, and every LLM when trained, they will be evaluated against those benchmarking data sets to prove that yes, they are trained well foundationally for next word and also trained well for the subsequent word subsequent tasks. Then these models are called as pre-trained models or foundation models. Means they are not trained on any specific domain. They are domain agnostic. That means they are generative models now. They know language. They know pretty much all tasks to some extent. They may be good at some tasks very much, but maybe slightly good at some other tasks. But in terms of domain specific data, they know all the domains, but they are not specialized in any specific domain. Okay, this is the state of all the foundation models. So as a text generation model, it works. You initiate a story, you write 4 lines of a story, give it to a LLM, it continues the story. Whether it is realistic, meaningful or not, that is second question, but it continues. It takes a break from the text. But if you expect it to work in a way that you are seeing in your domain, then you have to do one extra step further. Okay. Which is called as fine tuning of elements. That will become next. Uh, yeah, so coming back to the categories of elements built on transformers, one is the encoder only categories, which is bird like let's say bird like we have variants of bird is there, shield bird is there, D bird type is there. Okay, there are many such ones, the elements. And coming to the decoder only, so in the transformer, I forget about encoder, only stack up the decoders like always your network architecture. So such architectures have been used in another category of LLMs, which are the GPT, generative pre-trained transformers. Okay. So you might have heard of very well-known chat assistant today, the Chat GPT, which is basically trained initially on GPT 3, GPT 2, GPT 3, now GPT-4. So GPT is an architecture which is basically based on transformers, but using only the decoder. Okay, so you just stack up the transformer decoders, you input a text, it produces. Because you have seen that in the transformers architecture, decoders are the one which produce the text mostly, right? So GPT models are well known for their generative capability, for their ability to generate text. Okay, so that is how the chatbot, the chat GPT is so popular, and many LLMs that are trained after that could it be Llama, or could it be uh, Mistral AI today. So they are all on the decoder of the architectures. Okay. So these are the two different types of LLMs that you see in our present LLM literature. Okay. But basically they both are come from transformers. Right. I think I've already briefed on these tasks. So, with these powerful large language models present with us today, and IoT as a huge technology, how healthcare can be related by these two technologies is remote patient monitoring and support, like patient is present somewhere in the globe, and the person who is monitoring is present somewhere else. The remote patient monitoring can just happen with IoT data, IoT devices capturing this real-time information, sending it to the server, and server running the LLM kind of models which are capable of, kind of summarizing, generating, analyzing, predicting. Right? These are the capabilities. It can predict, okay, what is happening in this particular patient. Right? Does he need immediate attention? Okay, whom to inform? Okay, what sort of problem that is occurred? So you can think of language models capable of doing all these things given the data. But where the data should come from, the data should come from patient. How this communication can happen through IoT. Okay. So IoT devices sensors are attached to the patient. Could be like wearable as simple as that. And the hardware monitoring, your movement, your blood pressure, monitoring systems. They are wearable to the patient. Okay. To some extreme, this is where you have to have a patient in some laboratory, some systems which are mounted over there and TSME connected to them, and then monitoring happens here. But the data inferencing happens in some server, so which is connected via internet through this IoT device. Finally, decisions, all the things will take place there, and if this requires one person to be attended to inform, you can just trigger the information. Allowing for personalized health alert, as I said, if it is doing its job with respect to every person. So since it is seeing every person independently, it can give personalized recommendations. Okay. And other situations, symptoms provide immediate first aid. Right? So in majority of the health related problems, I can say is that mostly the first aid will be very important. Okay. If something wrong has gone with the patient, immediate first aid can help him like survive that. So the first aid, you should know what should be given in the first aid. You may not be a medical expert, but the first aid procedure could be very simple, but you do not know what should be done. Right? Because you do not know what is happening. So if you connect it to IoT and server which actually decides what should be done based on its expert training that you can give on to that. So it can decide what first aid should be given, and that first aid information can be given back to you who is attending the patient. He may not be a medical expert. He just knows, okay, this should be done now, he'll do it. That may save him from dying. So that is the kind of help that we see. And healthcare chatbots and virtual assistants. As I said, today you can see apps, your mobile apps, which have your latest information, and they recommend you what to be done. Or you can just ask it, like, I am feeling these symptoms. Is it really to be careful of, or should I say the doctor, or what exactly it could be. So it will respond you back based on its analysis of thousands of such reports that symptoms previously, and what doctors have decided based on symptoms, and what prescriptions was given, and actually the initial prescriptions, it's not the final, the careful given prescriptions. The initial prescriptions can be shown to you based on the analysis. So those chatbots are now available, are already in the market. Okay. So it can manage your medication schedule, it can remind you, you've not taken this. So if it is elderly person, chatbot will typically help them take care of their medications and everything, and basic healthcare advice. Predictive analytics and early warnings. So as I said, before something wrong happens, because like, for example, the cardiac, paralysis. So you do not know what is going wrong with your heart system, but in the sense that something like a wrong case of heart disease, then maybe it could be in a continuous monitoring with such device, and the sensor can continuously track various health parameters, and you can send it to the prediction server or the LLM which is doing the inference. And the LLM can predict, oh, he is into this situation already. The next that will be is this. He might get a cardiac arrest. Okay, in next few hours. So it can immediately alarm and based on that it can take certain action before that can happen. Right? So that is how the today's predictive analytics is being used to identify the health issues in advance based on the patterns. Uh, because generally it is not, all of a sudden it will not happen in your body. There will be certain pattern, after that only something will come out. So that pattern it can be captured through your model by analyzing the data that is sent across your IoT device, and that will help you in early diagnosis. So first medicine statement plan based on your medical history. Because in healthcare today, it is not just the medication or just the medicine that is mattering today, it is precision medicine that is required. For example, in the case of cancer tumor, right? Each and every person will have various levels of requirement of, for example, the treatment, the dosage that is given to him. So that has to be decided based on his condition, his history, how much was given earlier and how much is needed today, and how much should be given tomorrow, and what is his improvement over time. This everything monitoring for a medical expert who is attending to him will also attend to another patients will be very different. And he has to at least record them, go back and check and come back and decide. All these can be automated based on this data evaluations. So healthcare planning and education. So even the end users who would be like legal professionals who are in the early stages of their careers, they can be educated with the help of the IoT and based systems which have seen vast variety of experience, conversations, histories of all the medical experts in the area. They can guide, they can educate you on how and what is the correct best procedure that is being carried out. So that is also an advantage of IoT embedded analytics. Okay. Next. Yeah. So when it comes to how exactly I want to use the LLMs in healthcare, the simplest way is whatever is available, you can use it. Like if you just want to use it as your day-to-day chatbot to understand your simple health routines and your guidance for your mental health, then you can use the different ones because they know based on what should be your food diet, what should be these things for what reason. Okay, they can at least guide you on that different and certain symptoms. So if you say that I have a body pain and fever and something like that, it might be predict something. It says that this could be the potential reason. This is the initial thing that we can do. If it doesn't recover, you can approach it after, right? So even before you approach the doctor, you also know what should be done. At least you need not worry about the severity that will happen to you. So all these things can be done in a pre-trained LLM because they've seen so vast amount of data, they are not good. Second thing is, I am a healthcare professional, or my patient's case is very critical. It's not like all the symptoms, all day-to-day diseases that you see. They are very complex diseases which need detailed monitoring and close observation and very precise medication. Right? Even light fluctuation might lead to serious situation. In that case, you need an LLM which is fine-tuned or adopted to that particular domain and it has enough knowledge and sufficient background analysis on top of how it should be handled. So that is we call as fine-tuning on domain specific data. Okay. So when I say the domain system data, it is to capture such conversations, is records, different patients of such, everything. Okay. And then fine tune them and use them for the second thing is we have retrieval augmented generation. There, most of the time, what happens is fine tuning and LLM itself is a reading exercise. Um, and that mostly demands, if not very huge, but slightly bigger data. Like the LLMs are pre-trained using petabytes. I mean, let's say they are trained on hundreds of billions of documents. They are trained. Now I want to use it for my medical specific problem. Then if you want to fine tune it, you will, if not tens, hundreds of billions of paragraphs or documents, you will at least need thousands of notes of your domain, which are very clean. When I say clean, they should not have noise. They should not have cases where things have been wrongly treated and things have gone wrong. Those should be properly flagged. This is the wrong thing, and they should be avoided. So if that is not there as the negative thing, but as positive, then that's a noise. That's not clean data. So you should have tens of thousands of clean data with you of your problem to be used to find it. That's one challenge data. Second is it also requires a huge computation device to do the model fine-tuning. Okay. Third important thing is that if you do not have so much time dedicated to this, then you probably think of not doing it. Then the alternative comes is the in-context learning through few shorthand retrieval augmented generation. That is basically how we, I mean, you must have seen in your previous session by mostly, I think, Dr. Imran, where he must have shown you how to interact with LLMs through line chain, right? Where he has generated prompts and what are the responses that are. So in the prompt, basically prompt is the query that is going to the LLM. So that query mostly will be having an instruction, the data, and what is expected out of LLM, everything. And when I say everything, you can also pass some related content. Right? See, for this problem, these are the related documents that I have with me, and this is my current problem. Try to use these related documents and also your existing knowledge and try to retrieve back with a response for my question. So that is retrieval augmented generation. But to give you additional information, you should have either have that handy with you for your query, or if you have collected and kept it, but you are unable to find your model, but you just have the data with you, at least you can create a vector data with basically a quantity of this data points with you. And when you want to query or LLM for your particular question, you can look into that data repository for similar content for your query. Whatever you see as similar, you can use them as additional context to your LLM prompt and send it. Okay. So this will definitely improve the LLM response because When compared to using a retrained element, which has just seen the open world data, when compared to that, sending an additional context of your domain data along with your question will help them to align its response possibly more related to what exactly you are asking into your domain. Okay. So that approach is known as retrieval augmented generation. There is a framework basically to it. What we do is we create even in the branching framework we have like module where you can just ingest your data that you have in the repository, maybe like a simple Excel file that you have a queue with all the details, okay, mostly properly formatted. So the ancient kind of framework, they just take it, they create an index database which is easily searchable, I mean quickly searchable in real time. Something like search DB, where the search will happen almost in real time. It is not like linear search, which we already cards will be like in minutes of time. No, it is almost real time search based on different techniques. Simple could be hashing, okay, for having constant and such, right? So you have a lot of mechanisms today to almost achieve constant time search for similar value given from here. I have a query, I want similar content in my database. So that gets retrieved and that will not be retrieved as text, that can be retrieved as a vector also. If embedding can be directly retrieved. Basically the comparison happens to embeddings only and the vector database will have the embedding, basically the vector representation of each and every content that you have with you in your Excel or CSV file will be stored as vector embeddings in the database so that the computation can be faster. And so your query gets one embedding and all the corresponding embeddings of the existing content is there. You get a similarity matching and retrieve the top 5 or top 3 and use them, use the corresponding text of those into a LLM prompt and your LLM prompt has good context than just having okay asking this kind of question. So that improves the response of LLM. So this is an alternative to fine tuning an LLM on your domain system. Because fine tuning LLM comes with its own cost and complications, right? You should be an expert to write it, fine tune it, and do the evaluations and data creation, everything. At least that can be avoided to a certain extent. But I'm not comparing the fine tune model to pre-trained LLM, which is just with some supporting content. So I'm not comparing these two exactly, but it is an alternative. Okay, depends on like your use case. Sometimes they both work equally good. Sometimes one could be better than the other. So definitely it has to be validated and used. But this is the alternative. At least if not, perhaps if you do not have the pre-existing data that is collected and kept with you, I am very sure that for your question, if you are asking question, you are from that domain, you know something about that. You can generate few samples. Yes, you can say that. See, this is brand, this is brand, this is brand, this is brand. You can say that. You can generate some profile of that time. Add as few examples, just for a few short. Okay. I'm giving you few examples of how to decide on these kind of questions based on these analysis of these question responses that has been in future. Following this question, the new question, you try to answer me accurately, which is aligning with how I am formulating. Okay. So that is few short. More recently, like we are applying few short and that together to make it easier. And mostly, instead of arguing even in the industry level, what you do is directly use event elements with few short and that is approach because that saves a lot of time and timing and fine tuning. If that is doing good, we'll just use that and maybe over the time we'll have sufficient amount of data related to your level and you can just use that as a training data and like in parallel you can also do the fine tuning. So you'll have a ready to go model in your hand without fine tuning, just with few short and that. You can immediately go production. Then finally you can think of other finding the wrong. So that is one. Coming to using LLM on edge devices like low memory, low compute devices. Like the LLMs are so big, they require like 100, 200 substitutes of memory. How can we achieve that? Then there are quite a few approaches like even in the industry scale, we do not want to unnecessarily spend on compute. Even though we have compute, we want to optimize it. Right? On the other hand, you have edge devices which are already very low in the compute and memory. Then the optimization techniques could be like you can think of involving LLMs and trying conventional language models based on like RNNs kind of model. They may still work very good if you do not have the problems that they are not good at. Kind of like large sequence problem, which could be a problem in RNN, which has certain to some extent been handled in the related kind of architecture. So if you do not have that long sequences to be problems, then fine, you can go with the conventional one. And if you do not have very strong context understanding and additional knowledge based problems, like it is not just the data which you should decide, it should also have some sound background expertise, right? Like a person who has spent almost 10 15 years in the education history. That much of knowledge if you expect from the model, but the conventional models are not because they do not have whatever data that you are bring on, only that much information you have. In that case, if you go to LLMs because they are being trained as large amount of data, it is set up equal to experience of tens of 15 years of an expert. But not very, very fine grained to a problem which you have to handle. Okay. So you can think of training small models depending on problem type. Another is distillation. So which is very important solution to using LLM in a short, small size model. Is basically, as you know, LLMs are trained on vast amount of data. They know, I mean, general things, but I want it to be specialized. So the specialized person doesn't need to know. I am a specialized person. I do not know about finance. I do not have to know also. Okay, because I'm expert in this field. So why are you using an LLM, which is jack of all, so you are master of all? No, right? So what you do is, I want to take the knowledge that LLM has about this specific problem, take that only that part of the knowledge of LLM and use it in another model. So when you say only that part of knowledge, of course it is small compared to the entire knowledge. So here the knowledge means the parameters because the model has millions of parameters. Not all parameters are responsible for all of the tasks, all of the domains. Some domains will have only certain parameters which are maybe required for the model to make the decisions. Then you can think of deciding which those parameters are by asking the elements several questions and taking a response and seeing which parameters are getting activated, okay, which neurons are getting activated. Having only those parameters and removing other neurons and parameters from the entire architecture, maybe dropping from 70 million to 1 billion. Is really sufficient for my domain. I still have the same capability of the big element in a smaller model, which is good enough to run on my. So that is distillation. There are approaches, and the other approaches are in terms of doing the computation itself, right? So basically, the LLMs can train and use off the shelf. They work with flows, long flows. Okay, that means 16 and 32-bit and 64-bit representations. Okay, of the numbers, the real numbers. Uh, Okay, you need real numbers to have those precision values, right? After the decimal point. If I leave away them, then they are integers. Correct? If you leave away them, then probably you are losing some precision. That's for sure. But still, it is not completely inaccurate. Right? It is close to accurate, optimized, right? So I can achieve a near optimal model by just converting from float to integer computation and in the integer there is a 4-bit, 8-bit. So this is where the techniques like LoRa, which is LoRa adapters, and QLoRa, which is quantized LoRa adapters, they apply these onto LLMs in production. Okay. So you can fine tune an LLM using parameters. Then what the basically does is it tries to have the real implementations in features. By basically adding adapters on there. Okay. So that will reduce the computational requirement of your phone. Okay. So this is how you can take your LLMs to devices with lesser compute. Yeah, this is just an illustration of how library works. When the user asks a query that goes at the prompt LLM, in the case of that, in the query and the corresponding instructions, they directly do not go. Instead, based on the query, a search happens into the database of all the relevant content. From the database, the context will be retrieved, and such additional context goes as uh, uh, added something to the prompts that goes to LLM. And based on that, it produces better response compared to the existing. Right, right. So I think this is what I had as a content. I will try to quickly show a couple of illustrations if possible. Otherwise, I'll share the code. Till I connect my system, if anybody has any clarification. I may not be able to model, I'll just try to show you simple and
Wi-Fi, it was icons, icons, icons.
one thing is of course like I cannot run even the inference on my local laptop because of very size. So I'm going to use AWS service Bedrock through which I can access LLMs. Even mostly all the cloud providers they have their own way of serving these large language models that you can consume. If you basically are interested in doing the inferencing on cloud, you can go to any of the cloud providers and use their services. Um, so pretty much same even in even Amazon has its own way of giving you those LLMs access. It has a service called Bedrock, on which like a lot of foundation models, the LLMs and vision models available, which you can use through APIs. You can make requests to them and uh, based on the cost, and based on the model size, the cost is different. So I'm here trying to access one of the LLMs which is Anthropic. The provider is Anthropic. Uh, the model is model 2. So you can basically ask question to it. I have some data. this is a healthcare data. Maybe if anybody, any of you is interested in training model on healthcare data, you probably use this. There's a healthcare application, healthcare magic, from where data set of 100K will be created with annotation basically. Input is around what are the symptoms as explained by the patient, and output is basically the response from the medical practitioner. Okay. So you can use this to train your models to behave like the medical practitioners. And I will now trying to use the pretrained one. I give this information in the prompt now. Let's see, I mean, for this question that has been asked, what the LLM's response would be. I will remove the output from here. Just keep it in output expected, just to validate. I'm very sure that I won't be able to produce the exact same output, but maybe content wise similar. Remove this instruction. I'm just giving a basic, very basic prompt now. There are ways to optimize your prompts as well. Let's say, uh, imagine you are a physician. Just to set the context right, like I am asking the LLM to perceive itself as a physician. Uh, Please answer the medical questions based on the patient's description. Uh, Inside input. Okay. So let me just send this. And let me ask for the output to be produced. So I'm going to prompt the LLM with this input text. Let's see how it responds. So this cloud V2 is a LLM with very context length of 100K. Basically, context length is another important factor in LLMs. Why? Because when we are thinking of using LLMs with few shots and drag based additional context, whatever you send into LLM is the text that you are sending ideally, right? So if your text itself is of size, let's say, 5,000 words, your LLM should be capable of taking 5,000 words a day, right? At least. Otherwise, it gets truncated. If it is a model which is trained for handling only 1,000 words, basically we talk in terms of tokens, not exactly words. Let's say tokens to terms, you can say just for 100 words, we might generate 130 tokens. So more or so equal to words. So if your model is trained on less tokens than the input that you are giving, then the rest of the tokens after that length will be truncated and it will not be used even if you are using. And in some cases, the context length really matters to us because we have sufficient context to be given as input to train. Then if I am unable to give that context to LLM, LLM will not behave as I expect, so that will not be very useful for me. Second thing is it's very especially useful for conversational systems. When I say chatbots, your chat might be of say few days. For few days of chat with your medical application, you might have ended up with say 20K words if you just see your chat. For your client question in your chat, the LLM should refer to the entire previous chat before it produces an answer, so that it is very relevant to your question, so that it has understood the context properly. If it is unable to handle all the context of the entire previous chat, then that is not going to be very useful as a conversational system, right? Because this is very much important in the healthcare sector also, because the response of an LLM for a question posed by a patient should be taking into context the entire medical history of this. It should be quite big. So that is also an important factor in LLMs. And one of the recently the advancements that we are seeing in analysis, one is their accuracy in producing the proper output. Second is how big the text you can handle. Right? So the context length is also an important improvement that we are seeing today. And plot this V2 from Anthropic is a provider, basically is a company. They have trends model which can handle up to 100K context length. And nowadays we are seeing models which really do not take the 100K context, but they work for 100K context by doing some other optimization, right? So that's also in progress today. So, so it has responded back saying that it is sounding like you are having symptoms of vertigo. Let's just see the output. If we expected output, we have that vertigo symptoms positions of vertigo, right? So most likely your LLM, without any explicit medical training, is able to detect based on just the symptoms that were given in your input that it is the symptoms of vertigo, and so it has also guided you like the key points and what recommendation is given, so everything is being produced. So this is able to do to some extent, but maybe it will not suggest you an exact medication or treatment unless otherwise it is trained to do that and it is allowed to do that. So the other aspects of using LLMs is the governance of it. Are they can they directly be used as a replacement to experts, or they just be used as aid to the experts, right? Supporting to the experts. So that's a debate, and that is definitely dependent on the seriousness of the medical condition that is being posed to that event, right? So if it is a very serious problem, we definitely take not a replacement because it cannot bypass the human expert, at least for now, okay, in all the fields of the medical conditions. So, and I have a script where I can train an LLM, which I did. I'll just go over it. Definitely, I cannot train it. Here we are training using Google Colab. Basically, I just wanted to show that we can train some LLM using Google Colab also, which is free resource. But the only question is that you cannot directly use the fine-tune the existing LLM. Instead, you have to use some of the optimization that we talked about, like doing distillation, using distilled model, or doing optimization through LoRa-based techniques like right. So here it is through the use of LoRa that I am trying to find this 7 billion models on Google Colab, which is running a T4 GPU, which is a GPU but of very small capability. So how we can do is there are libraries. We just need to use them and specify that how many bits of operation you want to do. I'm saying that here, like I want to do a 4-bit quantization to my data, and these are the standard libraries for the interface where you just specify what model are you using, and extra configuration that is going is don't use the original model, use the quantized model to this quantization mechanism. And right, so here the different training arguments, the batch size, different type of parameters like number of epochs, batch size, which typically including number of epochs, and yeah, floating point 16, whether to be used or not. So we are not using them because I want to have optimized modeling for it. Uh, and as a monitoring tool, I'm using weights and biases. Weights and biases is a tool where you can just leave your model training monitoring process onto this tool, and it will just plot the graphs of training and everything in real time, and we can just observe from here. And also, you can track the different versions of your models with all the hyperparameters and other variations that you impose to the model. So just trying to use that weights and bias. Finally, this is being trained on a Wikipedia data set. So as you can see here, I could just do for some 4 or 5 iterations, as expected, the loss is getting reduced, which has been reflected in my weights and biases dashboard as well. As you can see here, it is showing this on the training loss and over the logs, and you can do different logs for your training. Basically, you are connecting your whole Colab output to this portal, and it shows it. I can share this offline if any of you are interested in it, just to explore how fine tuning it can. And I'll share that medical data set also, so that you can just try to use that data set for fine tuning, and we can really come up with a simple chatbot which can be used in the assisting of simple medications for different symptoms and identifying what the disease is. Right? And that's quite huge. Data set also, it is 100K in number. It's very real conversations captured from the particular application. Yeah, this is what I had from the demo. Thank you. And any questions, clarifications? I know it is a bit long discussion, but if you really have something to ask, or if something is not very clear, I know some of the content, like when I talk about transformers, you need sufficient background of deep learning to understand it very clearly. But I have tried to put the background also in picture. To some extent in the human time slot, but I know we'll definitely have a lot of confusions over there, which I'm very sure that if you are really interested, you can further explore on that part. But I just wanted to convey that the present day large language models that we're talking about are originated from transformers and attention mechanisms, because here today they are the one which are the the dominating component of any LLM. Apart from the minor extensions that you see in terms of optimization in the context and making them more accurate, right? Training and making them better at doing general intelligent tasks. Apart from all of this, the core architecture still has transformers as the backbone, either the encoder in case of BERT-like models or the decoder in case of GPT-like models. Okay, so right then, I think with that, I think it is more or less, aligning to the context of this program as well, because it is really a good topic to be discussed upon, and there are lots of work that is happening both in industry, and research wise. There are a lot of products coming up on one side, a lot of research happening on the other side, and which is ultimately benefiting the human community. So I wish, like, if some of you from this workshop take this as a trigger for you to work further on these areas, which will definitely help you and others in the long run. For that, I thank each one of you for your patient listening and thank the organizers and each and every one of this program. Yes, it is open for any questions.
Yes, if you have any questions related to this presentation, you can ask. If you have any doubts with respect to the presentation,
Yes, yes.
Changes from human and machine is basically the technology tools.
Correct.
And today I want to know that even the system is also forgetting. Self.
Yeah. Like if you are trying to expand your memory to remember, then you have applying memory, so we
LED
tend to forget things.
display
So
LED,
the systems also use
LED,
the and memory is
LCD,
less. If you are increasing the
AC.
memory, then they can remember this. Just the simple thing. That was the problem initially, like because the problem is because see every advancement in research has come in alignment with the technology. So earlier we only had CPUs, so even before that very low end devices, and the research used to happen only on those devices and only I mean the outputs were only capable of working on those devices. They connected their limitations. Even if the researchers think beyond that, they were able to showcase it or I mean do something with that because there is no technology support. They are already had it. They will be always trade-off. So definitely after the introduction of GPUs, this trade-off has changed to a greater extent, and we are seeing like the actually there is huge data hardware side as well. And definitely the cloud and almost have achieved what is required in terms of hardware, but it is coming with cost. Cost is the question. If you are ready to afford it, then you are good to go. If you cannot afford it, then you will think of substitutions.
Translation and transliteration is completely different. So are you working on transliteration?
So, as far as I understand, transliteration is along with the context.
Context is a language. I'm talking about translation is just whatever is there being translated, it doesn't have to have any prerequisite information about the language itself.
Correct.
Transliteration is it's like English being written in Kannada. Textual manner.
Okay, I got it. So the way we use in our messages later, right? Yeah, very good example. I think there are quite a few approaches. I mean, this is all down to the whole of just really what the so definitely translation is an important problem. So mostly the research is focusing on that. But transliteration, quite a few definitely. Like if you want to use what the data available today, not all data is native from. Like as you said, when you try to grab the social media data, at least in the social media data, I see a lot of transliterated text. It is an English text, but being with is not English, is Kannada, Hindi or something. Right? So there are approaches where especially this social media kind of problems are there. Like you would want to recommend a product, right? Social media. Mostly like in social media, you cannot expect a person, at least like a person in India, to always chat, do the conversation in native English. They mostly make it up, they go with translation, as I said. So mostly those organizations which are mostly focused on this are doing this part. Yeah, but research-wise, there may not be so extensive research, but in industrial research, there is. In industrial research, like parents will do their own research to advance the organs and the things, solution, everything, independent of problem or the kind of end application. Whereas industries they focus on a specific application which bring back the revenue to them. By doing so, whatever the research that has been done cannot be directly useful. They need to tweak it through further enhancements where leadership research can be done. I think there is a, I'm not very versed with that approach, but I'm sure that. Right, yes.
Citizen is NLP generative AI.
No, generative AI is what we are seeing a lot about today. But NLP is all about working with text. Like, you want to understand the text, like, probably not also thing NLP umbrella, classification is there, aggregation is there, even identifying extraction. Extraction is there, like you have a big text you want to extract and ready over there, right? And you have the application problem, right? The completions, you have the questions, so chatbots. So all these are kind of so are the LLMs are all developed keeping all these problems. But definitely the foundation model cannot be doing good in one aspect, which is why.
As I said, we have ready LLM models.
Yeah.
Run on AWS.
I mean, any cloud basically any LLMs are available. There are like two categories. One is publicly available open source LLMs, which the researchers or the organization they have tried and they have just open sourced it
Already
for
made
public
it.
use for the researchers, right? And even commercially useful. Some are proprietary, right? What OpenAI has produced, GPT.
ಯಾವಾಗ ಅದು ಟೆಸ್ಟ್ ಮಾಡಿ ಟೆಸ್ಟ್
So we can directly use for
ಆಗಲೇ 11:56 12:39
So every cloud provider,
ಅದು ಆನ್
they,
ಆಫ್ಲೈನ್
it has become obvious that because of the hugeness of these models, you cannot afford to have them on your computers and in your organization. Because you need to invest a lot in your hardware. So the obvious solution is having them on cloud by some cloud provider, you take it as a service. So only whenever you ask for the make a request to that LLM, you will be charged. On this basis, most of the providers are trying to give you the open LLMs also and also the paid version. Right, yes, for that. And I'm very happy to meet Professor who was my friend, classmate, and he's also Professor here after a long time.
So I take this opportunity to thank Dr. Mohammed Sohail so for the explanation of LLM and RAG, right, particular augmentation of generation towards the natural language processing. So here, I think in this presentation, you all come to know that so how exactly the LLM, large language models will be used in the natural language processing, and also RAG will be used in natural language processing. How we are using it and what is the procedure we need to keep on implementation process. In a similar way, we have explained with the implementation process, how we have standard libraries needs to be used to implementing the LLM. Okay. For example, if I want to generate generative AI, so what will the combinations I we need to use? For example, maybe the combinations like the array itself is telling that so it's a retrieval and augmentation of generative. Generative models and the retrieval models needs to be together. So I have for example, generative AI. Okay, so he has explained in detail with respect to step-by-step procedures also. So a great thanks to Dr. Mohammed Sohail and also he's a mentor like in so when you have studied MCA, so if you did not understand any of the concepts in the class, so what we are doing, so we just get into him and we are asking the doubts. So I did not understand the particular concept, please explain. So when he has explained the concept clearly, at that time only most of the classmates, maybe there will be about 5 to 6 friends over here. Okay, so we will be taking the clarification from him only. Whenever we have taken the clarification from him, at that time also we can able to understand the particular concepts there. So until that, and also what when I actually so when I started implementation at that time, even I don't know what actually a C program is at that time. Okay. So when I visited when I meet when I met Guru sir at that time, so we were in what in the lowest level of implementation. So sir has assigned so as so he needs to teach us the code as well as the explanation in the testing code. Whenever we have started the to means the example, if I say what is that A, okay, so what you will think is just an alphabet, but he will not think in that way. A will be he can able to describe it in different ways. Means his understanding capabilities will be in different ways. So that is what actually will be helpful for other unknown persons. Means if unknown person if he did not understand anything of them, definitely he can able to understand the things to them. So that's what the capability is. So, I can say I got it from my mentor teachers and my thanks a lot for that. Thank you very much. And I request Dr. Shishir to